Okay, so this is the, if you tried this lab yourself, or this is lab 2, the hints and stuff. Okay, so we'll kind of go through very quickly an outline of what's going on here. Okay, building up towards an Euler method program. Okay, if you need to do something mathematical very quickly, consider using the online computational tool Wolfram Alpha. We probably don't need that. I'm going to stick with the naming conventions. Don't just start writing code, have a think first. For your own code, it might be worth putting in comments. Certain computation we've done many times. Consider defining a function. We're probably not going to use a function. I know they would have been used a lot, but what's happening with us is that we're going to have too many arguments. So too many things to give an input to the function, so you'll be here all day. Okay. So now if you're doing this before the lectures in week, probably even week 2, you won't understand the theory yet, so you might have to wait until Tuesday week, something, whatever it is, the 2nd of February or something. Okay. Anyway, what I got is a differential equation. So you've got the derivative given in terms of x and y, and you've the starting value of y. This is an initial value problem. So some examples. The velocity of an object subject to damping force, where this is the acceleration. This comes from Newton's second law. So the acceleration, well, mass, if you multiply both sides by mass times acceleration, is minus lambda v. That's how a damper works. The damping force is proportional to the velocity. That's where the lambda, that's the constant proportionality. And at 0, you got an initial speed. Okay. Newton cooling, which says that the rate of change of temperature is this is when you've got something like a cup of tea in a room, or a ball bearing in a massive hot bath, something like that. I think the tea in the room is a better idea. So the change in temperature is proportional to the difference between the temperature and the reservoir temperature. So in other words, that's saying, for example, with a cup of tea, it will cool fastest when it's hottest, because the difference in temperature between the tea and the room temperature will be as large as possible. And then when that difference in temperature gets small, the temperature doesn't change that much. That's when you're approaching room temperature. And then here we have one, the shear force at a distance x along a beam subject to Gaussian loading. So that's a loading that is near the supports, is quite small, and then it kind of peaks in the middle. Okay. Now the number RA we might have to find with an integral, which is given there like that. But we can actually write integrals as initial value problems. So a lot of these methods can also be used for approximating integrals. Okay. So under nice conditions, they have a unique solution. Okay, this is theory, you can read that. This is basically Euler's method. I'm just going to have to assume that you've watched the lecture, so I'm going to drive on here. So we are going to do this, we're either going to look at the dampers, the damping problem, or we're going to look at, say, the temperature problem, or we're going to look at the beam. We're not going to do them all together, but we've got plenty of scope to vary. You can set up that you vary the problem parameters, the initial conditions, the range of values that you're interested in the solution, and the step size to increase accuracy. So these are all things we can do. Okay, so we're going to build up the functionality. We're going to kind of build up to a VBA program just by building up. So let's see how this works. So on worksheet 1, we can solve this specific problem. So I'm just going to call this rename W1 for worksheet 1. I might have been called that a second ago. Okay, so we're going to look at a specific problem. The velocity at time t of an object subject to a damping force given by the solution of this. Note the role of y is played by v, because like dy dx, while the role of x is played by t. So mechanical testing showed this damper brings the object to rest in under 10 seconds. In column A, under label t, input values of so that shouldn't be too difficult for us. You're going to have a label here, and you want to go from 0, 0.1, 0.2 all the way down to 10 seconds. Okay, in column B, label this with a V. Okay, input 0.2, the initial velocity. Where's that? Yeah, so that's the initial velocity. there. Now in cell B3, that's here, write code that does this. So this says that the next v value, so that's what it goes here, so it'll just be equals. The previous v value, which is 0.2, plus the step size. Now you shouldn't click this one because if we're dragging this down, it'll go 0.1, 0.2, 0.3, but the step size is always the same. So either you use some dollars signs to fix it at this one, or else I would actually just write in 0.1 times. Now what's this big fx? Well, this is the derivative, so we need to do minus lambda over m times v. So if I do minus lambda over m, with the minus 1.5 divided by 2, I get minus 3/4. Minus 3/4 times the previous v, because this is the slope at the previous point. So v1 is this point, v0 corresponds to this. I'm just going to put it in there. Okay, and just make sure I have that right. Yeah. Now in terms of this, like this little index here, so the index 0, 1, 2, 3, 4, 5. So this is saying v1, that's here, is equal to v0, that's here, the previous v, plus the step size, which was 0.1, times the derivative, and look, the derivative is evaluated t0, v0, that's these. Now the t doesn't come into it, but the v0 does, so I use b2. And then that's correct, and now you just, well, this will go down to 10 seconds, and you can just double click this one, and that will be you away with it. Okay, so that's kind of, we've done that really for you. So the next v, yeah, okay. Now it's v of t, which is just v, it's not v by t, so that's commented there. Drag the code down, produce the plot. Okay, that's that done. So obviously you can go and finish that. Next one, and so this is design. So what we're going to do here is say you have the problem, like I think it's going to be the damper again, and you have the mass, and you want to know how strong the damper is to be, so that you get the behavior you want. Okay, so we'll set this up. So in column A, I'm not going to do it completely as usual. I'm actually going to do a slightly different problem. But okay, so what's it saying? Do T, do V. So we need to go from 0 to 1 in steps of 0.01. Go down to 1, okay. In column B of this, put the initial velocity, which is 5, okay. In cell D1, write damping coefficient, and put in whatever you want, say 10. So what we're trying to do, if we read the problem, I'll let you read it, we're trying to, I think, get the speed in 1 second to be very, very small. And the question is, what should the value of the damping coefficient be to achieve that? Okay. So then what you do is you go off and do your Euler's method. It says the next value is the previous value plus the step size, which is 0.01, times the derivative, which is minus lambda. Now we want to fix on this, so it's written there. We do, how does it work? $d $2, so that's the lambda, over the mass is 0.1 times the previous v, which is this. Okay, now I'll let you finish it off yourself. It looks like 10 is a bad choice, by the way. Yeah, but we won't worry about that. Okay. Now drag the code down, produce a plot, and then do this. Okay, so I'm going to do an example of this. So I'm going to do a different situation. I'm just going to do maybe X. I'm just going to show you this goal seek. And let's say that this will be the y0. And we're going to do dy dx equal to x squared, for argument's sake. Okay, so put in 0, 1, 2, 3, and we'll just go down to 0.1. And say the initial value of y. Now this is a slightly different problem. So this time what I'm varying is the starting y to get this equal to something in a certain time. So it says pick a starting value of say 1, for argument's sake. That's how it's there. And what I want to get really is I want to get this to be 10. Okay. Now I'll actually I can put this y0. That's the initial value of y. I can actually just put that here. Okay. And now I'll do my Euler's method. So Euler's method says the next y value is the previous y value plus the step size times the previous slope. Now the slope is x squared, but the previous x is over here, x squared. And now I bring that down. Now I want to get this equal to 10. So what I'm going to do is I'm going to vary the initial value of y until I get what I want to see, which is y of 1 equal to 10. Now that's an abstract thing. I just want to show you how the goal seek works. So it's kind of written here. You go, what if, was it data, what, data analysis, I'm in the wrong place, am I? Data, where it is, what if analysis, goal seek. So we want to get this equal to 10 by changing this. And this, and I'm not sure even how they do it. There's various different techniques. Around, so I must contain a formula. Ooh. Okay. Okay, the issue is that I dragged both of these, which is wrong. Because this one doesn't have the formula, it's just this is the formula, so that's all I wanted to drag. Okay, so it'll work properly now. So what if analysis, goal seek, set this thing, I want that to equal 10, and I'll do it by changing the initial value of y. And watch what it does, flick, 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 and it gets there eventually, and it does what you want. So you're going to do something similar to that. Okay, so now we're going to go into VBA. Right, put labels T and V, T, V. Okay, open up worksheet 2, blah, blah, whatever, and write a subroutine. So we want to get, the easiest way to get into our code is to, okay, here's the starting value. Yeah, so for our launching our code, usually it's nice to just do a button. This will open it up. We want to do option explicit in case we misspell any variables. And now we want to get this thing into our head where there's going to be kind of the same structure from now until the end of the semester. So the first thing is you define variables. You have to have a little think about how many you need. Then you give initial values to the variables. And then you're going to have a big loop, which is almost certainly going to be a do loop. And in the loop, you print the current values of the variables, and you calculate the next values. That's basically all that we're doing, okay? So let's see here. So in terms of variables in this problem, so it's going to be like the damper again. I think we are going to okay, I think we're going to do the same problem. It's not actually clear here. Unfortunately, it's not one bit clear, but we're using this thing. So yeah, we've got all these things. Should we, yeah, we're going to use specific values. So we're going to use lambda is 1.5 and m is 2. Okay, and maybe at this point we won't include them as variables. Yeah, because we won't include them as variables at this point. So what variables do we have? We've got the velocity, we've got the time, and the again, you could say the step size, but at this time we won't. We'll keep it simple. It's just velocity, time, and the counter. Because we're doing a loop, we're going to need a counter. Okay, so the variables will be the time, dBLT, as double. You can name them other things if you want, but the dBL is called dBLV as double. That just means kind of it can be a decimal. And then the counter should be an integer whole number, dim int c. Now what I'm going to do is, when we can, if the counter corresponds to rows, we'll call it int row. as double. So there you're starting things. Now the, sorry, not a double, an integer. We'll give them their starting values. So the initial value of t is 0. Now it's missing a 0 there. The initial value of v is 0.2. And the initial value of the counter, we're thinking of it as a row number. And I think what we're going to do is we're going to start going into row 2. So we're going to give the initial value of 2. Okay. So now we're going to do our loop. Okay. So what's the loop? Okay. So it's going to, so what does it say? It says do something, something, do this, and loop until or while. We're going to go from 0 to 10. So now here it says when using double, use loop until it's smaller or bigger. How about loop until the time is bigger than 10? That should be good. Okay. Now how we print the current values, I'm just going to do the time here. Cells, so you go row, int row, so that's the row number, and then time is in column 1 equal to dblt. So that sets puts things in column 1 equal to the current time. And then we need to calculate the next value. So you get dblt is equal to the previous time plus the step size, which here is 0.1. Now you're going to have to do the dblv yourself using Euler's method. And then very important, you have to put the row up by 1. Int row equal to int row plus 1. I should recommend to you that if you're going to run code, especially that you've just written, you really probably should save it before you run it in case there's a mistake. Now here I'm going to just say we run it here. Now this will just do the time. I haven't actually included any of the V's, but there we go. You might see it going slightly above 10. That might just be a bit of rounding error. I wouldn't worry about it. I'm going to delete it again and just this. You do have to understand this code, and like it's not rocket science. It's hard when you don't get it, but when you understand it, it should be quite clear. So if you want to understand code, you do F8, F8, F8. So we go line by line. So now we've got all these variables defined. So it's going to put the value of t equal to 0. Now, see the way it's 0 already, that's before it's, they're all 0 by default, and then you reassign them. So now the value of v is 0.2 and the row number is 2. So now at the moment the row number is 2. So this is cells 2, 1, row, that's 2, 1, row 2, column 1, that's here. And it's going to print that equal to the time, and the current value of the time is 0. So there you get your 0. Then the time goes up by 0.1, it goes from 0 to 0.1. And then the row number, which is currently 2, goes to 2 plus 1 is 3. Now what's the current time? At the moment it's just 0.1. Is the time bigger than 10? No, so we loop. And then it's the same, and now we're on to the next row, and then it just keeps on going. Okay. So that's into VBA done. Now, then there's something about recording macro for automatic deletion of data and graphs, highlighting of data, insertion of new graphs. Now, some of this is a little bit messy, but it's very useful. So what I'm going to do here is I'm going to do a little VBA Euler method just in parallel here. So this is x and y, and we're going to do the one we saw before, dy, we'll do dy dx is equal to x plus y. Okay. So x is 0, and we'll start y at say 1. And we'll go down 0.1, 0.1, 0.2, 0.3. And what I'm showing you, there's going to be kind of clever ways of doing. See, actually, I don't want to do that. So I'm going to do a new button just for this one. So, so a lot of it's going to be the same. So I'm just going to copy and paste all that. So the variables are going to be not t and v, but x and y. The row is going to be the same. The initial x, I said, what did I say, 0. Initial, so the x, initial y, take it to be 1. And, okay, print this. Now this will be in column, if you look at the x's, it's in column 4. And that's dbx. And then similarly, cells int row column 5 equals dbly. That's the next x value. We're going to go up in 0.1s, and we're going to go until x is bigger than, say, 2. Now I have to do Euler's method here. So the next y value is equal to the previous y value plus the step size, which is 0.1, times the previous x. Now we've got a little bit of a problem here, but it's good I can actually show you something I'm going to have to think about. Now I'm going to eventually, I think, show a different way of using, you see, Euler's method says dy dx at the previous point, so I need the previous x and the previous y. Now the previous y is no problem, do that, but look at what's happened to x. As we go down, right, and I'll just put in dBLX, which is wrong at the moment, and then we'll fix it afterwards. Okay, so we'll do this line by line. This one here, F8. So initial x is 0, initial y is 1, intro is 2. Print the starting x, starting y, that's done. Then you calculate the next x value, which will go to 0.1. And now we're calculating the next y value. And we do next y is previous y, that's fine, plus step size. And then it should be the previous slope. Now the slope is x plus y in this differential equation. But look, what is the previous x? It's 0. But now this line has changed the previous x, so we've got a problem. Now, I think you could just swap the dBLX and the dBLY. I think that will just do the job, but I'm going to show you kind of a thing that might be a bit more common. The thing is that we actually have printed the previous x. So rather than using dBLX, we could just take the printed version off the worksheet. And this now is the previous x, 0. And now that will work. Now there's a number of ways you could swap the x and the y, that would work. You could, then there's another way we use arrays. You could do dBLX minus 0.1 to go back to the previous or whatever. And now we keep going, this will now work. Don't know, did I change it on time, so maybe I'll stop. Okay, so start it again. Okay, F5, right. So this is this. Now here you see it stopped a little early, that's due to rounding, but don't worry too much about something like that. I mean, you can always just, okay. So what I want to show you here is some special functionality. So you're going to be running these things multiple times, and you're going to be changing things like maybe the initial value of y, for example. And what might also happen is you might change the step size and how far you run. And what's happening basically is you want to run something like this, but there's say you go to 2 and say previously I went to 4 with a different y, and I didn't want all that stuff down there. Well, what you want to do in that case is you want to write code that before you run anything, it actually deletes this, deletes all of this, and maybe puts in a new x and puts in a y, maybe actually selects the data for us, and maybe even inserts the graph. Maybe we want to do all that. Now there's some messing around here where we're going to get, there's some little subtleties, but the basic idea is all I really care about. So, how I'm going to do this, just to illustrate it, is I'm going to put a little, I'm going to change the final time here. So I'm going to add an additional variable. So dBL final time as double, and I'm going to give that as an input box. dBL final time equal to, actually I'm not going to do an input box, I'm going to put it in here, F2, which is cells 2, row 2, column 6. And we're going to run it until it's bigger than dBL final time. So this is the kind of thing we're going to see. So I'll put the final time here, T final, say 1 here. Now, like if I run it there, and in fact I probably want this to be variable as well. Let me do that as well. So we'll do the initial value is user defined as well. So we'll put that here. developer. So the initial value of y will be cells row 4, column 6. Okay. So we can change these two and get different stuff. Now I see here what happened. We ran it with the starting speed of 2 and we only went up to a final time of 1 second, and we got just nonsense. If you look at it, like if we graph this is nonsense, right? So what you want to do is you want to be able to, before you run it a second time, select this, delete it, put back in your labels, and run the code, then select it and put in a graph. Now they're easy things to do in Excel, but what you can do is there's something called the macro recorder that allows you to, where is it? I might have to go to the large screen. Yeah, here it is, macro recorder. That will allow you to do things in Excel and record the code as VBA. So I'll show you how it works. So everything I'm going to do from now on, so this is going to be called delete the old. And there's different ways you can do this, and new labels. So I want to get rid of the previous junk. So I take these, delete. That's the last run of the data. Then put the labels back. Now stop the recording. We'll see in a minute where that is. And now we want to highlight the data to insert a graph. There's slightly better ways of doing this, because what's going to happen here, I think, is every time we run it, we'll get a new graph where you won't worry about now. Highlight and graph. So how would you do it? Well, once you've run it, you select both of these, isn't it? You insert this and say we like this graph. Okay. Now the way we're doing it is it's always going to keep giving you new graphs. It's possible to delete the old graphs and do other things. I'll let you figure that out yourselves. Stop recording. Now, where are those bits of code? Well, if you go into your modules here, there. I think you can actually just, so there's two things you can do here. You can just copy and paste the code. So this is the one that deletes the old data and gives you new labels. Or I think you can write call. I think you can write call. Now I'm not as good as, say, Bob at this kind of stuff, so I should be careful. So I'm going to try call. If it doesn't work, I won't feel too bad. We'll simply copy and paste then. Yeah, so I'm not a good programmer as Bob at all, so just let you know that. Okay, so now we'll go line by line on this F8s. So F8, so delete the old and the new labels. Does it do that? Okay, it comes to the module, fair enough, it's going to do it. Selects everything that's there, deletes it, puts in the new labels again, finishes, goes back here. Now it does whatever, and it runs itself off. Now we're going to time 2. What happened there? Something bad happened. No, nothing bad happened. It did exactly what we wanted. So now what we can do is, rather than messing around, we can just change this, say the final time, change it to speed, press it. I think it's still stuck in here. And we get a new graph. Now the problem is, I think every time you're getting a new graph, but that's a worry, I'm not interested. Now, what am I really showing you here is this macro recorder. Okay, so it's really handy for doing stylistic things. We'll see it a bit more later on. Okay, now back to the problem that we're actually working with, which is this thing. What we're going to do is we're going to make lambda, which is a damping coefficient, the mass, and I think the initial velocity, and eventually more and more stuff user defined so that you can change them and run the program again. So let's see, suppose we want to change the mass, in this exercise we'll continue. So we're going to continue working on this code, but we're going to boost it up. Now what I'm going to do, I'm going to just go into the next thing. So this is parameters and initial conditions. Parameters and initial conditions. Okay, so what I'm going to recommend here actually is that you set up a what I might call a dashboard here, something like this. Okay, so we're going to kind of rob the code from earlier. Now it's just not big up with this code because it's got the same kind of look. And the name is probably wrong, so let's insert the button maybe here. So command button 1 is the name of it. Okay. So what are we going to do? So we're going to have just 2 additional variables. Now we're going to have more and more and more. So I'm kind of, yeah, we'll just run it. Yeah. Okay. Yeah, let's do this dashboard. So let's do mass lambda, and let's be a bit fancy. Put a symbol here. Maybe some Greek lambda there. Okay. Try and do them. Anyway, it doesn't go back the same way. Okay. Are we going to do any more here? So we'll also do the initial velocity, which you could actually call u, for example. Now it's going to be pretty much the same story, but we're going to get things from here. So say mass equal to 1, lambda equal to 2, initial speed equal to 2 for argument's sake, doesn't really matter. Okay, 2v. Right. So we've got additional variables here. We've got the mass, dim, dBl mass as double, dim, dBl lambda, I'll just call it big L, as double. You want to give them all initial values, so T and V are sorted. V, now we're going to take from the dashboard, cells 2, 8. Similar story, I'm not going to do the whole thing for you. You're going to have initial values of dBl m equal to take it from your little dashboard, dBl L equal to taken from your dashboard. Okay, now things are going to be kind of similar enough down here. You must also print V, and then here you must also, oh yeah, that's already right there. Using the Euler's method now, what you're going to do, you have to be careful, you want to do, I'll kind of set this up for you. So it needs to be something like dBlV is equal to dBlV plus the step size, which is 0.1, and then your derivative minus lambda m over v. So something like, now in your own proper code, minus lambda over m, with obviously dBlm. See, I don't want to do too much for E. Times the previous b. And keep looping like that, and that will do it. Okay? So, and then you can just, if you want to get the thing I showed previously that selects and deletes and reselects and graphs or whatever, you can include that. And then what you can do is you can just change these and press the button and it runs again. I think actually the easiest thing to do is to do the deleting and the reprinting the labels, and then don't bother with inserting the graph in the macro recorder, because I think if you just do this, then if you run it, it'll automatically graph it for you, which is a bit easier. Okay. Now the next thing I think I'll probably leave to yourself. So you're going to do the step size and the range. So you're going to beef up your code now. So this will be step size, range, and automatic selecting, which we've already done. And so you're going to have H in your console, your dashboard, and also your final time. These are also going to be user defined. And so again, what you're going to be doing, the code is going to be very, very similar. But you're just going to incorporate, you won't be using point 1 in the code you'll use DBLH, and you won't be using until 10 or whatever, you'll be doing until final time. I think that is pretty much everything. Here's the contents of A and B. There might be easier ways of doing that, but probably for the macro recorder does all this. It sets initial value t equals 0. Yeah, okay. Then once you have it, you can see what happens with these. Now the same problem as before, that's, I'm not sure what that is at the moment. We won't worry about that. Answer the following questions. I'll have to put the answers to these into the assignment, which I will. So yeah, I'll put the answer. This I will. Yeah, I'll put all answers so you can check your answers as such. Now some of them might be in the final video. Choosing a smaller step size is costly in terms of running time. The next few lectures we're going to come up with smarter methods than whatever. Okay. Now the exercises, probably what I'm going to do is I'm going to probably put those, because they're very similar, I'm going to put them in a different video.